everybody, this is Rudra Pradhan here. Welcome to Engineering Econometrics. Today we will continue with modeling diagnostics. In the last couple of lectures we have discussed something about linear regression modeling, and that too in a bivariate framework and multivariate framework, and we have discussed a kind of engineering problems where the problem may be with two variables, where one is dependent variable and one is independent variables. And we have also discussed a scenario where we have one dependent variable with multiple independent variables. While doing the kind of predictions and forecastings, that is with respect to dependent variable and independent variables. So, the step by step process is very simple. So, we have to fit the model, then estimate the model, and after the estimations we have to go for the reliability check. Once the estimated model will pass through reliability check, then we will go for the prediction and forecastings. But by the way, in the process of discussions we have gone through various test procedures, starting with specification test, goodness of fit test, diagnostic test, and out of sample prediction test. These are all for main test through which we can apply in the estimated models to check the reliability before you do the prediction and forecasting. In the last class we have discussed something problems relating to the specification test and the kind of goodness of fit test, and also slightly we have discussed about the out of sample prediction test. The diagnostic test part is not yet covered. So, we will discuss the details of that particular test in this lecture, and it is not a simple component. It is a kind of it is like complex kind of structures. We have to pass through various types of test under the diagnostic test, and then we would like to check, and we finally declare that the estimated model is okay for the prediction and forecastings. So, let us see how is the kind of structure, and then we can proceed. So, this is what is all about the simple linear regression modeling, and that too in a kind of multivariate structures where we have a dependent variables and we have couple of independent variables. These are all called as k independent variables. So, now dealing in multivariate problems, that to multiple regression modeling. So, we can actually express many things, and our testing structure or testing procedure will be more effective, and to discuss the kind of engineering problems, and that to predict the engineering requirements and forecasting the engineering requirements. So, let us see how is the kind of structure. And what I have already mentioned, that once you pick up the particular problem, so the standard procedure is to fit the model, estimate the model, and then go for the reliability. Once it will be passed through reliability, then you can go for the prediction and forecasting. So, whatever we have discussed till now, so this is something like this. The first part of this particular discussion is the CLRM, that is classical linear regression modeling, and then the technique which you apply to estimate the model is called as ordinary least square methods, that is OLS, and then the reliability of the estimated model will typically called as blue, that is the best linear unbiased estimator, and it is followed by a theorem called as a Gauss-Markov theorem. And all these items can be covered, and that too with the help of the assumptions of ordinary least square mechanisms. So, now the reliability of the estimated models by the OLS mechanism should satisfy all the assumptions, otherwise it will go against the reliability part. So, what we will do right now? We will discuss all these assumptions behind OLS, and a particular means if you go one by one of these particular assumption, then we will find a couple of issues will arise, and these issues can be actually checked and then finally clean before we go for the estimation and forecasting. So, now what will we do here? Let us see means the assumption of OLS. So, first assumption behind this OLS mechanism is the model must be linear in parameters. We start with the various structure of the model. Simple, you can write like this: beta 0 plus beta 1 x 1 plus beta 2 x 2 and so on, and every time these parameters are linear, but that does not mean that variables will be linear. So, we may have a function and that functions may be in any form, but the parameters which will be connected to this particular modeling, that is a classical linear regression modeling, which is actually estimated by OLS mechanism. So, where parameters should be technically linear in nature. Then second point is the independent variable of error, means independent variable is independent of error term. So, that means technically in the process of estimations we have three kinds of variables. So, one is the dependent variables, then the second one is independent variables, that is known to you, that is called as explained, and then independent unexplained variable, which is called as u. So, now the second point talks about the relationship between x and u. So, that means technically there should not be any covariance between x and y. Then third one is the mean value of the error term should be 0. So, which we have already discussed, because the line of the best fit or the estimated line will pass through all the points where 50 points of the observation will be above and 50% observation will be below. That is the difference between actual y and estimated y, and the points which are above than estimated lines where the error term will be positive, and the points which are below than estimated lines where the error will be negative. So, now sum of these positive errors and sum of the negative errors should be equal, and as a result sum of the error terms should be equal to 0. If that is the case, the particular line can be called as the best fit line, and that too OLS is valid for this particular estimation. Then we have constant error variance. So, where once we will find out the error component, then we have to find out the error variance. So, the error variance should be constant over the time or any cross sectional unit. If that is the case, then this is good for the OLS and good for the reliability. If the variance will differ from time to time and different cross sectional units, then this will go against the OLS, and as a result the particular model cannot be reliable one. Then no correlation between independent variables. So, that means technically we have two sets of variable, typically multiple regression case or multivariate case, where particularly in the case of multiple regression we have a dependent variable with a series of independent variables. So, where we have the declaration that these variables are independent. So, as a result technically there should not be any linear relationship among these independent variables. If that is the case, then it goes against the OLS mechanism, and by default the model will not be reliable. So, it is against the reliability. So, means as a result the particular model cannot be used for prediction and forecasting. Then no correlation between error terms, typically like two independent variable will not have any relationship. So, similarly error term is also independent variable here, and like x 1 and x 2. So, there will be u and u 2 means cluster of error terms which may be in the form of different cross sectional structures or different time series structure by using the lag concept, and as a result the requirement is the correlation among these error terms should not be something positive or negative, it should be exactly equal to 0. If that is the case, then the model will be reliable and it is in favor of OLS. If it is actually not equal to 0, it goes against the OLS mechanism. Then no correlation between independent variable and error terms. So, technically there are three kind of structure. So, between x and u, then x x and u u. So, okay, so you just put I j and this is let us say I j. So, like this. So, these are all 3 different clusters we have to check, and in all the cases the covariance or the correlation should be equal to 0. If that is the case, it is in favor of OLS. If that is not the case, then it goes against the OLS mechanisms. As a result, the estimated model which is derived through OLS mechanism is not at all reliable, and as a result the particular model cannot be used for forecasting. And then finally, the sampling structure where the sample size should be substantially greater than 2 k, and then there should not be any outlier in the system. That means, outlier is a kind of data point which is a highly distant from other data points. If there is a outlier, then typically the points which you have discussed, like correlation between independent variables, then correlation between error terms, then correlation between independent variable and error terms, and the kind of constant variance, or the kind of mean sum of the error, whatever may be the items which you have discussed. So, it will get affected. So, as a result, so the outlier problem should be drastically checked, and then go ahead with the kind of prediction and forecasting. So, we have to see whether there is outlier. So, if there is outlier, so there are 2 ways you can solve the issue. Either you remove the outlier without affecting the sampling, or else you keep the outlier, but do the kind of transformations, different ways of setup, so that the influence of outlier, particular outliers may not affect the modeling structure drastically. And the simple logic is that means after going through all these assumptions, the simple understanding is like that. If the assumptions are violated, then the model cannot be reliable. So, that means the estimated model will pass through all these assumptions before you declare that the model is a reliable one for the, or the best one for the prediction and forecasting. So, that means the particular assumptions or all these assumptions should be satisfied before the prediction and forecasting. So, if that is not the case, then the OLS mechanism may not be applied. So, we can look for some different mechanisms like generalized least square methods, weighted least square method to estimate the particular process, and then go for the kind of prediction and forecasting. Since OLS mechanism is very simple, very easy to understand, very easy to pick up. So, in the first instance, we have to apply OLS and then do the estimations, then check the reliability and go ahead with the prediction and forecasting. If it goes against the a kind of diagnostics or the OLS assumptions, then by default we have to think about the restructuring or re-estimation process. Otherwise, this is the simple way to estimate, check, and then proceed for the prediction and forecasting. So, likewise, we have to be very careful all these scenario, then we have to discuss the details about this scenario. So, that means technically whatever we have discussed till now, it is the problem identifications, then model building, then model estimation, and that too with the help of typically OLS techniques. So, once you use OLS technique or apply OLS technique to have the estimated model, then the estimated models will pass through all these assumptions. If that is the case, then the particular model is called as BLUE. So, that means it is called as a best linear and unbiased estimator. So, this is the case here. So, BLUE stands for best linear unbiased estimator. So, that means we start with the model simply y equal to beta 0 plus beta 1 x plus u, and then estimated model will be beta 0 head plus beta 1 head x, and so these parameters or these estimators should be actually free from all errors and finally declared as best, that is or goes through BLUE theorem, that is best linear unbiased estimators. So, it is popularly known as a Gauss Markov theorem. So, that means if you go if you just connect with the assumption and the kind of requirement, then the theorem tells like this: given the assumption of the classical linear regression model, the least square estimators in the class of unbiased estimators have minimum variance, that is there blue. So, that means, so whatever values of the parameters we have received through the estimation process, it should be called as best, and followed by linearity, unbiasedness and minimum variance. So, that means, the parameters should be technically free from all kinds of errors. Then we will call as best. So, once the parameters will be declared as the best, then by default the estimated model will be declared as the best, and as a result you can use this model for prediction and forecasting. So, this is what the Gauss-Markov theorem, and now if the Gauss-Markov theorem will not valid. So, that means, the particular model is going against the OLS assumptions, either few or all or something like that, then in any case model cannot be declared as the best model, or the line cannot be declared as a line of the best fit. So, now let us start with this. Since means this is a class of diagnostic checks or diagnostic structure. So, what will you do? So, we like to point out what are the diagnostic we are supposed to do before you declare the model is a good fit, and the model should be used for the prediction and forecasting. So, combining all these assumptions, so we are supposed to discuss all these problems. So, the first problem dealing with this particular process is called as a multicollinearity problem. So, here the issue is about the relationship among the regressors, that is the independent variables. Then heteroscedasticity problem. So, that is the correlation variance of the error terms. If the variance of the error term is a constant, then this is the declaration of homoscedasticity and good for the OLS mechanism and good for the model fit, and then you can use for forecasting and prediction. If the error term is not error variance is not constant over the time or cross-sectional unit, then this particular problem is called as a heteroscedasticity problem, and it is a typical virus in the modeling process or estimation process. So, before you use that particular model for prediction and forecasting, so it should be free from heteroscedasticity problem. That means, it is simply called as heterogeneous variance. So, which is against the OLS mechanism. So, because OLS mechanism requirement is error variance should be constant, and if that is the case, then that is called as homoscedasticity. That means, technically homoscedasticity is good for the OLS, and heteroscedasticity is against with OLS. So, we have to see whether we are in a heteroscedasticity structure or a homoscedasticity structure, but there may be the problem may be in between. So, but we try to restructure, re-estimate, redesigns until unless you get the model in such a way that it is free from all kinds of error. Then the third problem is the autocorrelation problem, where we like to check whether there is a correlation among the error terms, not the variance component, it is the covariance component. For instance, suppose there are two error terms, then the error term then we can write a covariance matrix like this y 1 y 2 and u 1 u 2. So, then we will have a 2 into 2 matrix. So, this is sigma square u 1 and this is sigma square u 2. So, this is sigma u 1 u 2, then this is sigma u 2 u 1. So, now this part is the homoscedasticity part, that means sigma square u 1 should be sigma square u 2. So, if that is the case, then its declaration is homoscedasticity, and if that is not equal, then it is the signal is heteroscedasticity. Okay. So, in other case it is a covariance between these two error term, and that is the case of called as autocorrelations. So, if you simplify with normality structure, then you should be closely connected to a mean 0 and unit variance, and as a result this particular matrix should transfer into unit matrix. So, if that is the case, then that is good for the OLS estimations and good for the model building, model estimations and the kind of prediction and forecasting. So, that means technically So, you are supposed to prepare two different metrics or two different kind of testing. So, one particular testing is with respect to all independent variables explained and all independent variables unexplained. So, two different metrics you have to prepare like this, and then check what is the status of the particular estimated model. Then finally, you can also establish the relationship between u and x jointly, whether there is a kind of relationship, and for that the requirement is there should not be any relationship between y u and x. So, to summarize, so there should not be any relationship between x x I and x j, many no relationship between u I and u j, and again there should not be any relationship between u I and x j. So, that means x upon x, u upon u, and x upon u or u upon x. So, these are the kind of possibilities. So, these relationships should not be there in the OLS estimation process while using OLS technique to predict the particular dependent variable with respect to independent variable. Then model selection criteria. So, even if you are fixing a particular models, then going through estimation process by OLS technique or other techniques. So, there are certain criteria is there to see that this whether the particular model is okay for the prediction and forecasting. Sometimes what happens, even the model is free from multicollinearity, heteroscedasticity, autocorrelation and other diagnostics. So, still you cannot say that the model is actually good for the prediction and forecasting. So, when we have actually couple of models by applying the robustness structure, then you have to finally select a model which is very good and which is actually very much useful for prediction and forecasting. So, when we have a n number of models with different structure and different kind of features with the same variables and the same problem, then ultimately it is you to decide which particular model finally will be picked up to go for the kind of prediction and forecasting. Ultimately, you are not in a position to use all the models to go for the prediction and forecasting. Out of several models, you have to pick up a particular model which is useful for the prediction and forecasting. So, which particular models you will pick up, so that needs actually model specification kind of structure. So, it depends upon many things. So, typically model selection criteria, consequence of the model specification errors when it is high. So, how you have to deal, test of specification error, errors of measurements, incorporate specification of the model. So, in addition to the problems like multicollinearity, heteroscedasticity, autocorrelation. So, these are all the additional kind of features you have to check, and these are called as model diagnostics before you declare that the model is completely free from all these virus, and then you can use this model for prediction and forecasting. So, since we have two different units for model diagnostics, so then we will go one by one. So, starting with first multicollinearity problem. So, we have to go through in details about the multicollinearity, what is exactly the particular items and how is its features, how to detect, how to cure, and whether it will go with model building or model estimations, or we need to clean it completely. So, these are the things we are supposed to do before we go for the prediction and forecasting. So, let us see how is this kind of structure. So, that means technically, so these are the major model diagnostics, and then we will start with the multicollinearity problem first. So, as we have already discussed, multicollinearity is a problem of independent variable, since it is a kind of structure where we have one dependent variable with many independent variable. So, these variables should be technically independent. So, so that means technically multicollinearity is a kind of game where we like to check whether there is a linear relationship among the regressors or any relationship among the independent variable. So the issue is very complicated, and let us go through by first the features of this multicollinearity. Then you think about the detections and the kind of tolerance and the kind of the solutions, and then the kind of overall structure of the model validations. So, first feature of the multicollinearity is it is the linear relationship among the independent variables, and then it is a multivariate problem, and that means technically we have two different setups which we have already discussed. One setup we have a two variable, one dependent and one independent, another setup we have one dependent with many independent, but ultimately in the second case the problem of multicollinearity can be detected, and where we have a many independent variables. That means multicollinearity can be checked when a model involves at least two independent variables. Otherwise this problem may not be there in the system. For instance, if you use bivariate modeling for any kind of prediction and forecasting, by default the kind of multicollinearity will not arise there. So, third point is the existence of linear relationships. So, we are not looking for nonlinearity part, and we are checking the linear relationship among the regressor by using either covariance or correlation or any other advanced criteria through which you can get to know whether there is a relationship among the regressor and how is this particular relationship, and that is the a kind of degree through which you can actually predict the environment. Then then independent variables should be linearly independent. So, that means technically if you go by vectorial algebra, so so far as a multivariate problem is concerned, so the variables in the multivariate setups are two different clusters. One is the linear dependency and linear independency. So, if these variables are linearly dependent, then this is having actually multicollinearity problem. If these variables are linearly independent, then this is having no multicollinearity problem. So, we like to check whether the basket having independent variables are linearly dependent or linearly independent. So, our requirement or OLS requirement is that these variables should be linearly independent, but in reality you may not find that particular situation, because reality is something different. So, as a result, so you will not find that all these independent variables are actually linearly independent. So, there is some relationship, and we try to check whether the relationship is statistically significant or it is at the tolerance levels. If it is going above the tolerance levels or statistically significant, then it is a major issue. So, before you go for the prediction and forecasting, you first actually thoroughly check the particular items and try to clean the particular virus, and then go ahead with the prediction and forecasting. Then finally, no issue with the nature of the relationship. So, since multicollinearity is the existence of linear relationship among the regressor, so far as a correlation is concerned or covariance is concerned, so the relationship can be tracked with correlation coefficient and covariance coefficient. So, we have no business whether the correlation coefficient is coming negative or the covariance is component is coming negative or correlation coefficient is positive. So, if the particular item is actually statistically significant, that means the correlation coefficient, whether it is a positive or negative, is coming statistically significant, then this is a major issue. So, whether it is a positive nature or negative nature, so that is immaterial, but ultimately we like to see whether the depth of relationship or the existence of relationship, linear relationship among the regressors are statistically significant or not. If they are statistically significant, then this particular models cannot be used for prediction and forecasting. So, we try to minimize this particular 0, even you cannot make it 0. So, it should be very low, so that we can actually validate the kind of models and then go ahead with the prediction and forecasting. So, now ultimate issue is actually how to go ahead with this kind of detections, means that means technically we have a two different environment altogether. In one situation it is 0 and another situation it is 1, like probability. So, when the independent variables are Li linearly independent, so then this is the case of means this is the situation of 0, and when they are linearly independent completely, then this is the case of 1. So, that means so the game is one extreme is 0 and another extreme is 1. So, when the linear relationship among the independent variables are coming actually 0 in each case, then you are in good track, but when it is coming actually 1, then that means technically it is a perfect relationship among the regressors, and that is completely wrong track. But in reality you may not actually 0 situations or 1 situation, you may be in between. So, in between means whether you are actually above 0.5 positively or negatively, or below than 0.5. Even if it is below than 0.5, that is the correlation coefficient, still you have to check the significance level. Until unless the particular component is statistically significant, you should not use that particular model for the prediction and forecasting. So, how you have to detect and how you have to proceed for the kind of solution, we will discuss in details in the next lecture. So, in the meantime, we will stop here and have a nice day. Thank you very much.